Ohm's law says that if a current I is passing through a conductor across which there is a voltage V applied, then V is directly proportional to I. Means as the current in the conductor will increase if the voltage across the 2 points A and B is increased. So the voltage is directly proportional to current. If the voltage is decreased, current will also decrease. So now this V can be written as R into I. I am converting proportionality sign into equality sign. So R can be written as V by I. V by I. This is called resistance. The unit is volts per ampere. We can roughly write as ohm, which is represented by, correct. So this is one of the very simple and important law which you must know if you have to solve important problems in physics. We'll talk more about this when we will deal with this subject in detail. Now the other thing which we will talk about is resistance in series. Resistance in series means I have three resistances. One is this, one is this, and another is this. We call it as R1, R2 and R3. There are three resistances. Now if I am connecting their ends to each other, I am connecting these ends. So if this is an end to end connection is called end to end connection of resistors is called series combination. This is called series combination. Okay. Now, if in this case a current I is flowing through it and I am applying a voltage V across this entire system, then I can write, and there is an equivalent resistance Req of the entire system, R1, R2 and R3, which are connected in series. So the formula I can write as V is equal to nothing but R equivalent into I. This is as per Ohm's law. Now another thing is, as we know from Ohm's law, this is also clear that there is a voltage drop V1 across this, there is a voltage V2 which is dropping across this, and there is a voltage V3 which is dropping along R3. So I can write as per Ohm's law, V1 is nothing but I into R1. V2 is nothing but I into R2. And V3 is nothing but I into R3. But you can see from this figure, that V is nothing but V1 plus V2 plus V3. Very simple. So I will put Req into I, which is as per this is equal to I into R1 plus I into R2 plus I into R3. I will cancel out I, I, and I. So what I will get? Req is nothing but R1 plus R2 plus R3. So in the series combination, equivalent resistance is nothing but the sum of all resistances connected to each other. The point to remember is the current is same. The current is same across all the resistors, which is I, and the voltage is different across all the resistors. This is important to understand. Now we come to other topic, which is resistance in parallel. Parallel means if there is one resistance R1, another resistance R2, and the third resistance is R3. If one end of all these resistance if I connect to each other and other end if I connect to each other, I will call it as point A, this is called as point B. Then we say that this combination is a parallel combination. Parallel combination. And again, if I apply a current I through it, of course I will go out from here. There is a voltage V across this. So I will divide the whole current is divided into three currents I1, I2 and I3. And as per Ohm's law, since voltage is same across all the resistors, so V is nothing but R1 into I1, V is equal to R2 into I2, and V is equal to R3 into I3. But here I is nothing but I1 plus I2 plus I3. You can see the I is divided into three currents I1, I2 and I3. So I is nothing but sum of all the three currents. So I will use this and this to write I1 is nothing but V by R1 plus V by R2 plus V by R3. And if Req is the equivalent resistance of this entire combination, then Req into I is nothing but V. So I will use this to write I. This is V by Req. Now, this V gets cancelled. 1 upon Req is nothing but 1 upon R1 plus 1 upon R2 plus 1 upon R3. So, in case of a parallel combination, the equivalent resistance is governed by this formula. So, you students should remember these two formulas. One is this, another is this. These two formulas will help you to find out the equivalent resistance for which we will talk about of the various combinations, which may not appear to be very simple when we see them at the first instance. Now, the third topic which I will be talking is Kirchoff's law. It says that if the many currents are coming and converging or meeting at a point I1, I2 and I3, and then they are diverging, into different currents I4, I5 and I6. Then definitely the sum of the converging currents at a point will be equal to sum of the diverging currents. These are converging currents and these are diverging currents. This we call as law of conservation of charge also. Now we will talk about the second Kirchhoff's law. I am drawing a very simple circuit with a battery which has a voltage V and there is a resistor connected to it. This is a closed loop. Once the loop is closed, then only the current will flow through it. We'll discuss all about this in detail. And now, when the current is flowing, current will flow from higher voltage to the lower voltage. So it is plus and minus. If in this circuit, the sum of all the sum of the voltage within a closed loop is equal to 0. So if I go in an anti-clockwise direction, you see that in this case you can undertake any direction as positive or negative. For simplicity, I am taking when I am moving anti-clockwise direction. In the battery, we are moving from low voltage to high voltage. That is, voltage is increasing. When the voltage is increasing, I am considering this as positive. And here, when we are moving, the voltage is decreasing from plus to minus. The voltage is decreasing. So I am taking here as minus. So this is nothing but R into I. And within a closed loop, the sum of all the voltages is 0. So I can write V is equal to R into I. So R is nothing but V by I, which is Ohm's law. I have already explained. So I have considered a very simple circuit to explain the Kirchhoff's law. But there will be very complicated circuits which are going to come when we solve the problems. Okay. So to understand this, I have taken very simple things which will help you to find out the equivalent resistance of the various combinations of circuits. So we'll take first example. First example. First example, I am taking in hexagon. I am taking in hexagon. Now, I'll use the same fundamental. Current I is flowing through it. There is a voltage V across it. And if Req is the equivalent resistance, if Req is the equivalent resistance of the entire combination, then V is nothing but Req into I. Now I am dividing this current I into X current here. There is a Y current which will go through it, and since you can see there is symmetry in the Y direction, the Y current is flowing here by symmetry. I will just write by symmetry. By symmetry I am writing the Y current will also pass through this. Now this Y current at this point gets divided into another current Z, and here it comes to y minus z. This is the current. Now you can check, now you can understand from the symmetry. This is y, x is flowing here, y is going here. Okay. Then from symmetry, the same currents has to meet here because it's a symmetric figure. We will make use of the symmetry and thus y, x and y. So from this you can understand that x current is going here and x current only is going into this. So whatever current is coming in this direction, it will go like this. It will go like this. So in this case, y minus z current will flow through it and y minus z plus z will again make it a y current, which I have written. So same will be the case here. Here also y minus z, it will flow here like this. So it will be y minus z. This is the z current and again they will make to make it as y. Hope you would have understood how the currents are distributed. This we have made use of the symmetry. Symmetry is very important. If you understand the symmetry, you can whatever currents will go out, they will meet, because there is a symmetry. There cannot be any difference in the current if there is a symmetry. The current will distribute itself in such a way so that it maintains its symmetry. So I will now redraw this figure. I is the current. So here it is divided into x. This is y. This is y. This is z. This one is y minus z. Here it will flow again y minus z. Here it is again y. Here it is again x. Here it is y minus z. This is again y minus z. This is z. This is y. See, I am writing plus minus plus minus plus minus plus minus. In the direction of the current is plus, other direction is minus. So I will make use of any one loop. I will take this loop as 1. If I use this loop and go clockwise direction, what I have done while I was explaining about the Kirchoff second law, this is a closed loop. This entire thing is a closed loop. So I am using the same concept plus to minus, then it is plus to minus, then it is minus to plus. So plus to minus, the voltage is decreasing. So I will use minus y times of R because the resistance is R. It is decreasing. Now for this also, you can see I am redrawing it. From this also, the voltage is decreasing from plus to minus. So I will write minus y minus z R. And in this case, it is increasing. So I will using plus x into R is equal to 0 because the sum of all the voltages in a closed loop is 0. So R gets cancelled. I will write minus y plus z plus x is equal to 0. So it is nothing but minus 2y plus z plus x is equal to 0, or I can write z plus x is nothing but 2y. So this is the relation between the three currents x, y and z. So I will go to another loop 2 where we have y and z currents to find out on the same basis. I will apply the rule of the Kirchoff second law, and on the same basis I will try to find out a relation between y and z. So if I go like this, In this, I am going from positive to negative, so it is decreasing. Here, negative to positive, it's increasing. So I will take out this, I will just come out here and redraw this so that there is no confusion. Y minus z, y minus z, and this is z. So it is plus minus, minus plus, this is plus minus. So this is 2. If I go into this, plus to minus, R is the current, R is the resistance. So Z into R, plus to minus, it is decreasing. So minus Z into R, increasing, minus to plus. So Y minus Z into R, and then here also it is increasing, plus Y minus Z into R is equal to 0, because within a loop the sum of all voltages is 0. Hope you would all be knowing why I am writing Y minus. This is current, this is resistance, which is equal to, this is current into resistance, which is voltage as per Ohm's law. Just for revision I am writing, so that you understand everything. Now here again I will cancel out R and R. So minus Z plus Y minus Z plus Y minus Z is equal to 0. So that is 3Z is nothing but 2Y. 3Z is nothing but 2Y. So if I make this equation 1, this 2, very simple. I'll put the value of 2Y in 1. So I can write this equation as Z plus X is equal to 3Z. Z plus X is equal to 3Z. Okay. So X is nothing but 2Z and Y is equal to 3Z by 2. So all the currents have come in the form of Z. So the total current will become, total current we know it is nothing but X plus 2Y. X plus 2Y. So X is 2Z and 2Y is 3Z. So this is nothing but 5Z. So the total current is 5Z, because 2Y is nothing but 3Z. So 2Y is 3Z, X is equal to 2Z. The total current I is 5Z. Okay. So I'll come back again to this. I have written V is equal to Req into I. So I can write as V is equal to R equivalent into 5Z. Y equivalent into 5Z. Now the interesting part in this is, if I travel, because voltage drop along these 2 points A and B is fixed. So in whatever path I travel, if I travel by this path or this path or this path, any path, the voltage drop will remain same between A and B as per the figure. So for the simplicity of finding out the equivalent resistance, and that also you all the students will have to do, choose the simplest path. So I am choosing the simplest path, which is this path, where the voltage drop is X into R plus X into R. So voltage drop will be between A and B along the middle path will be X into R and X into R. Okay. Means if I go like this, I am leaving other things. There is a X current and resistance R, and here another resistance is coming. This is another resistance, this is another resistance. This will be so X current is flowing and we are reaching at A and B point. So between A and B, I am leaving all other. So what will happen here? The voltage drop will be XR, and in this case also, here also, it will be X into R, because R is the resistance. So the total voltage drop across A and B, which is V, is given by 2XR. But X is, if I put it in terms of Y, X will be nothing but 2 times of X. I have written as 2 times of Z into R, which is 4ZR. So I am equating this with this. 4ZR is nothing but REQ into 5Z. So here ZZ will cancel and REQ will be nothing but 4R by 5, which is nothing but 0.8. So for this combination, equivalent resistance, which appears to be very tough, but by using the simple rules, because if you practice them, it will not be very difficult and time taking for you to find out the equivalent resistance, which is 0.8 R. Req is not 0.8 R. Now if you come to another example, I am just taking half of this. So now from the symmetry, you understand between this point A and B, if there is a current X flowing through it and Y is going to it, so by symmetry Y has to meet here, X has to come here, then only they will meet here. That means the current will flow from here to here. So we can simplify always. This can be simplified because you have done the problem earlier, so you can always write. So this will be nothing but it has no connection with it. So this will be R and this will be R. So this is R, this is R, this is R, this is R, this is R. Because current is flowing through it, so we can always detach them. So we see here that these three are connected. Two are connected in series. The total resistance, now I will use the formula of series and parallel resistance. So this one, this combination, and they are connected in series. So I will write for first limb, it will be R plus 2R into R divided by 3R. 2R, R plus R, this is in series, so 2R into R divided by 3R. How they have used the formula? There are two resistances which are connected in parallel, R1 and R2. Then equivalent resistance Req is nothing but R1 into R2 divided by R1 plus R2, which is nothing but actually if you solve this 1 upon Req, you will get 1 upon R1 plus R2. So the same formula will come. So 2R will be the series, so I will make it as 2R. This I will make as 2R. This is R and 2R into R by 2R plus R 3R plus R. So this I can write as R plus R plus 1R gets cancelled. It will become 2R by 3. So if I so solve this, it will become 3R plus 3R plus 2R. It will be 8R by 3. And the other is the sum of this is 2R. So I can further simplify this into simple what I have written as it is 8R by 3 and another combination is sum of these two R plus R, sum of these two because they are connected in series, it will be 2R. Okay, so it will become 2R. So this is point A and B. So now the equivalent resistance I will use the formula 1 upon Req will be 1 upon 8R by 3 plus 1 by 2R, which I can 3 by 8R 1 upon Req 3 by 8R plus 1 by 2R. I will take 8R as an LCM. It will become 3 plus 4R. 3 plus 4, not R is will not be there. So Req, so I will write Req is nothing but 8r by 7. So this is very simple. Hope you would have understood the entire concept of how to find out the equivalent resistance by making use of the Ohm's law, the formulas for resistance in series and parallel, and then Kirchoff's first law and the second law. So if you practice, you will can do it in much smaller time. So for today, this much is sufficient, and we'll discuss more about these topics when we will cover these chapters in detail. Thank you.